Hello, Algebra students, and welcome to our very first lesson of this unit on functions. This lesson is called Describing and Graphing Situations. In this lesson, these are our two goals. The first one is I can explain when a relationship between two quantities is a function. This idea of what a function is going to be a huge idea in this lesson, but also in this unit because the name of this unit is functions. So we're going to talk about a lot of different types of functions. Our second goal is I can make sense of descriptions and graphs of functions. So once we understand what a function is, we're going to be looking at lots of descriptions and different graphs. Again, not just in this lesson, but in this entire unit. And so today's lesson really starts the conversation about functions and what graphs and descriptions of functions look like. But we're definitely going to continue to work on these two goals throughout this unit. The warm-up is something you can do without knowing what a function is or any of that. The warm-up is about a bagel shop and related to this information over here. I encourage you, go ahead, pause the video now. And the question you are answering here is at the bottom is, can you explain how all four of these people, the shopkeeper, Jada, Priya, and Han, could be correct? Can you explain how they each figured out these prices? Go ahead, pause the video now, read through the information, and come back when you think you have an answer. After you've read through the story, you see that all four of these people came up with different costs using this information over here about the price of bagels. The shopkeeper says it's $16.25. Jada says it's $13.25. Priya says it's $13, and Han says it's $11.25. And they've gotten four different prices for the cost of 13 bagels. There is a way using this information over here to come up with those four costs. The first one, the most expensive one, the $16.25, you can get that by just using the cost of one bagel. You could take the cost of one bagel, I'm just going to label that, that's our one bagel, and you can multiply that by, we need 13 of them. And when you do that, you get the cost is $16.25. And there's nothing wrong with doing that. That's one way you can calculate that cost. But our second person who got $13.25, they did something differently. Instead of just using one bagel, they used those bags of 6 bagels. And so they said, if you want 13 bagels, you could get a bag of 6 bagels for $6. You can get another bag for $6. That's another 6 bagels. So now we have 12 bagels. And then our final bagel we need to get to 13, that final bagel, instead of grabbing that bag of 6, you're just grabbing one individual bagel for $1.25. And if you add all of that up, you get that $13.25. So they were using those bags of 6 bagels to get them to 13. Our next person, though, who got $13 wasn't using the bags of 6 bagels. They were using a bag of 9 bagels. And so you could start by grabbing a bag of 9 bagels. And if you do that, that costs you $8. Now we want a total of 13. So if you have a bag of 9 bagels, you need 4 more bagels. Now you can't grab any more bags. You're going to have to do those individual bagels. But you could do the cost of one bagel. That's our one bagel. And we said you need 4 more. So we want 4 of those. And if you do that, $1.25 times 4, that equals $5. And $5 plus $8 gets you to 13. So that third person is using the bags of 9 bagels to help them get 13 bagels. And then finally, our last person, and we're seeing the cheapest way to do this. If you want 13 bagels, the easiest way to get there is first grab a bag of 12 bagels. If you want 13, you have almost all of them right here, and that is $10. And then after that, if you want 13, you just need one more bagel. and that one more bagel is $1.25. And so that gets you to $11.25 for all 13 of them. So we're seeing from this, there are 4 different ways presented on the screen that you could calculate the cost of 13 bagels. Everyone is correct, right? Everyone's correctly using this information. Everyone is correctly adding. But it's just a matter of how you get to that total of 13. Thinking about this information and how you're using different combinations of these, I asked about 13 bagels, but if I had asked you to find the cost of 11 bagels, it's going to be similar, where there's a lot of different ways to calculate it. And what I've done down here is I have a table showing those different ways of calculating. So the shopkeeper, right, remember, he was the one who wasn't grabbing bags. He was just one bagel at a time, $1.25 for each of them. Jada was the one who said, let me grab the bags of 6. Priya said, let's grab a bag of 9. Han said he was grabbing the bag of 12 and then just adding one on after that. And so we see from this, not just 13 bagels, but a lot of different bagels, there's more than one cost you can come up with. And if I asked you, how much does 11 bagels cost? Do you have an answer? Well, if I look at the table, 11 bagels, the cost depends on how you're calculating it. There's not any one answer to that question. We see there are 3 different prices depending on who's finding your cost. There is a different question I could ask, though. Instead of me asking what's the cost of 11 bagels, I could ask you, what's the best price for 11 bagels? And there you might have an answer for that question. The best price is $10.50. That's the cheapest option. And similarly, I could ask that about other numbers. I could say, what's the best price of 8 bagels? And you would say $8.50. What's the best price of 13 bagels? $11.25. So if I'm just asking what's the price, we're seeing there's a lot of answers. But if I ask you the information in the second table and ask you what is the best price, there is only one answer. This idea of how many answers there are to these questions is related to the focus of this lesson today. And I'm going to say everything I said again, but just using some math vocabulary here. In this situation, the number of bagels you were talking about, we're going to refer to as the input. That is the information I'm giving you, right? I was saying, what if I buy 10 bagels? What if I buy 13 bagels? That's the information I'm putting into the situation. And from that, the thing you can figure out is the price or the best price, depending on what you want to look at. That is the output. So we describe the price or the best price. That is our output. That's what I was talking about earlier with the answer. So if our output is referring to price, we're seeing there's a lot of different outputs you can get. But when our output is best price, there is only one answer for that. So depending what information we want our output to be, you might have a lot of different outputs or just one single output. All of this is related to our definition of functions. The definition of a function and what this entire unit is going to be about is relationships between 2 quantities where each input has only one output. And in my notes that I'm sure you're taking as you watch this video, this is the part I would really emphasize. Is functions are relationships where each input has only one output. Using that definition, can you figure out which table above is a function? Each input has only one output. Which one of these tables is our function? The function is going to be the second one here. That is a function because each input, each number of bagels, has only one output, has only one best price for it. whereas this first situation, we're seeing that there is multiple outputs. There's nothing wrong with that. It just means that it is not a function. The focus of this unit is on situations like these here, situations where there is only one output. That is what makes something a function. The other thing we said we were focusing in on today, if I think back to our goals, we said we were going to learn what a function is, but we also said we were going to be looking at different graphs of functions. And so before we leave this story about bagels, I want us to think about what the graphs of these two situations would look like. What would it look like if I was trying to graph the number of bagels I buy and the price I could get versus graphing the number of bagels and the best price? Well, I've already graphed these for you, but we are going to graph our own later on. The graphs for these two situations look like these. So focus in on this first graph for a moment. This first graph is looking at the number of bagels you buy and just price. Not best price, just the price. And you're noticing you might just be looking at this saying, that looks crazy. And I agree, it does look crazy. Because when I look at this graph, I see at 11 bagels, I see 1, 2, 3 different points. And if I go back to that table we had looked at, that's exactly what we saw in the table. 11 bagels has 1, 2, 3 different prices. 11 bagels, that input, has 1, 2, 3 different outputs. Maybe in a past math class with a different math teacher, you've seen graphs like this. But with me, we have never seen a graph like this because this graph doesn't make a lot of sense, right? It would be weird if you walked into a store and said, I'd like 11 bagels. And they said, pick your price. It's any of these options. This doesn't happen a lot. The reason we're so focused on functions is because the second situation is a lot more what we're familiar with and makes a lot more sense. The second graph has the number of bagels and the best price. And this is the one we said is a function. And I can see it's a function from this graph because each input, each number of bagels, has only one output. There's only 1 point there for each of those, not 3 or 4, like here at number 13. And so this is something else we're going to see as we continue to look at different functions and look at graphs of functions. Is graphs of functions look something like this. Each input, each number on my x-axis has only one output. There's only 1 point there. This is not a function. And I can see that from the graph. I can see on the graph that at different inputs, like the input 7, I can see there is more than one output. I can see there are 2 outputs there. That's telling me 7 bagels can cost like $7 and cost like $9. I'm estimating those numbers from the graph. So this right here is what we're focusing on in this unit and in today's lesson. The goal of this first part is to introduce that definition of a function. And so, like I said, that key piece that we're going to keep using in this lesson, but literally every future lesson, is something is a function if each input has only one output. And I would strongly recommend that you put that in your notes. This definition is also going to be what we need to answer some questions for the second part of this lesson. So I'm moving us down. The second part of this lesson is all about this story about a dog being tied to a post. The second part of this lesson with this story, we're going to be actually creating different graphs to go with these and then answering some questions related to what we've been learning about functions. I encourage you, go ahead, pause the video here to read through the story and then come back to see some of the questions we're going to do with the story. Okay. After you've read through this story, you see our story is about 3 different days where a dog is tied to a post. We are given the information that this leash, this green cord the dog is tied with, the length of this is 5 feet long. And we are also told these 2 bullet points are going to be true for all 3 days. Every single day, the dog was 1.5 feet away from the post when the owner left. So even though that leash is 5 feet long, the dog can be closer to the post. And so when the owner left, the dog is 1.5 feet away. And then 60 seconds after the owner left, the dog was 4 feet from the post. So the dog must move in that first minute because he's now further away after 60 seconds. That is true for day 1, day 2, and day 3. What we are going to do is, using a little extra information about each day, we are going to create a graph to go with the situation. This unit on functions, it has a lot to do with graphs too. And so this is going to be our first chance to practice this idea of creating our own graphs from stories. So down here, I have all of the same information as above, right? The dog is tied to a post. The leash is 5 feet long. Each day, he's 1.5 feet away from the post when the owner left. And each day, 60 seconds after the owner left, the dog was 4 feet from the post. All of that's the information we saw above. I've gone ahead and I've created a graph for us for day 1. Day 1, the extra information I have is on day 1, the dog tried to follow its owner but was stopped by the leash. Then it started walking around the post until the leash was completely wound up around the post, and the dog stayed there until its owner returned. There's a lot of information here, but you have some freedom with the graph you created. But I want to talk you through how I made this graph first. The first thing I did was I used the information from these first 2 to mark 2 different points. I knew that the dog had to be 1.5 feet away from the post when the owner left. When the owner left is talking about what time? Well, when the owner left, it's talking about the beginning. It's talking about at 0 seconds. So I knew on my graph I needed to have a point right here at 1.5. I also knew at 60 seconds, so I'm over here now at 60, the dog had to be 4 feet from the post. So I had to also put that point right there. Now the rest of this, the blue line I put in, that's the part where I had some freedom, but I need to keep the story here in mind. So the first thing I've got is the dog tried to follow its owner, but was stopped by the leash. As I'm reading through this, I really want to be thinking about time and distance from the post. I want to be thinking about our X and our Y axis. So as I'm reading through this, if the dog is trying to follow the owner, what is happening with time and what is happening with distance? Those are the questions I'm asking myself. Well, as soon as the owner walks away and the dog starts to follow him, time is going forward. So I'm thinking about, as my line moves forward on my graph, as my line is showing that time is passing, what is happening to the distance? Well, if the dog tries to follow the owner, that means the distance is going up. The dog is walking away from the post. So notice my line goes up. I made my line go up pretty quickly until I got here. Why do you think I stopped here and I didn't keep going? Ideas? Well, it's because it says it was stopped by the leash. We said that leash is 5 feet long, so it can't go past 5 feet. If this is the post and the dog is pulling as hard as he can, there's my dog. The most he can be is 5 feet away from that post. He can't be any more than that, or else that means he's not tied to it. So my line had to stop here at 5. After that, all the story said is the dog is walking around the post until it's completely wound up. If this is your post and the dog is going around and around and around, maybe this has happened to you or a dog at some point, but if you keep going around and around and around, it's getting tangled. And what's happening to your distance as you do that? You're getting closer and closer and closer. So as he goes around and around and around, that dog is getting closer to our post. So notice my line had to go down. I had to show the distance is decreasing. I knew my line had to go through this point because that was our bullet point here. But then the rest of it, I just had it going down. I don't have it going all the way down to 0. At 0, it would mean like the dog is pushed against the pole. But I do have it decreasing the rest of the way. That could have looked different depending on who drew it. Maybe you had the dog following the owner a little slower, and then had it do something like this. That would be okay too. But I know it has to go through those 2 points. I know my line has to go up to the 5 until it was stopped by that leash. And then I do know that the distance has to go down after that. If the dog is going around the post, that distance, that line needs to go down to show the distance is decreasing. So either of those blue lines could be good graphs for this. Like I said, I did day 1, and I've got days 2 and 3 for you to try. So for day 2, you've got a lot less information, which means there's a lot of correct graphs you could draw. Don't forget, for day 2, these 2 things are still true, and you're going to use this new information about day 2, that the dog walked around the entire time while waiting for the owner. Again, pause this video, try to create a possible graph for this, and then come back to see how you did. I hope you've tried this one on your own first. Coming back to it, the first thing I would do is the same thing we talked about for that last one. I know the dog is 1.5 feet away from the post when the owner left. So I know my line has to start right here. That everyone should have the same. And I also know 60 seconds after the owner left, the dog was 4 feet away. So I also know my line has to go through that point right there. The rest of this line just has to show that the dog is walking around the entire time. I have had students who said, well, day 1, this graph meant the dog was walking around the whole time, and they drew a really similar graph. They said, okay, this is the dog following the owner, and then the dog turns around and starts getting closer to the post, and then ta-da! And that works. I mean, this is a graph of a dog walking around the entire time. He walked as far as he could and then walked back to the post. And it took him 160 seconds to do that. That would be fine. But there's a lot of other graphs you could do for this too. I'm going to draw a couple and get some thoughts on how you feel about them. Do you think... What about this one? Do you think that's a possibility? Is this a graph that shows the dog walking around the entire time? This graph does show the dog walking around the entire time, but there is a problem with it. Remember, we said the furthest that dog can get away is 5 feet. So our problem is right here. That dog is somehow getting further than 5 feet away. And so my line can't go above that 5 right there. So I could do something like this, and that would be okay. What about if my line did this? I started it similar to the other one, right? So this is the dog walking away from the post. Now this is the dog coming back to the post. What's happening here? If I think about it using these words, right? Time is moving forward. Time is passing. But here, where is the dog? The dog is 0 feet from the post. Where's the dog here? 0 feet from the post. Where's the dog here? 0 feet from the post. What is that dog doing then? That dog's not moving. If we want our dog walking around the entire time, I can't have something flat like this. I can't have that horizontal part of the graph because that shows the distance is not changing. The distance isn't going up. It's not going down. It's staying the same. And the distance can't stay the same if that dog is moving. So The problem with that graph was that second part. You could do something like this. That dog's being a little silly, right? But that works, right? The dog is getting further from the post, then closer to the post, then further from the post, closer to the post, further from the post. That's a nervous dog. I think that's a dog that just keeps going back and forth between that post. But that's a dog that's moving around the entire time. I've got one final one for you. I want that dog moving around the whole time, right? So what if my dog does this and they have to go through that point, and then they do this. They are moving the whole time. What do you think of that graph? Maybe you already have some thoughts, but to help you, I have a question. According to this graph, where is the dog after 80 seconds? Well, according to this graph, the dog after 80 seconds is at maybe 1.5 feet from the post, but the dog is also 3 feet from the post, but the dog is also 4.7 feet from the post. This is saying 80 seconds after the owner left, the dog is in 3 different places. That is not possible. The dog cannot be in 3 different places. So there's something wrong with this graph. And I've had students in the past describe it in a great way. They said when your line turns back, remember this x-axis is time. So when your line turns and starts heading back, that means you are going backwards in time. You cannot do that. So this is the dog going forward in time, right? 60 seconds, 80 seconds, 100 seconds. When you curve back like this, that's going backwards in time, 80 seconds, 60 seconds. You cannot do that. And it's not something you are going to see in any of the graphs we have in this unit. My line needs to constantly be going forward because time goes forward. So you can have a line that's really curvy like that, right? If you want it to be. But see how I'm always moving forward? My line has to keep going this direction because you can't go back in time. There's one final one. This one, again, I encourage you read through this and pause the video and try it. But I think we talked through a lot of different scenarios on that day too. So this last one we'll do a lot more quickly. Go ahead, pause the video and try day 3. For day 3, I'm going to start it the same way. We still have that same information about he starts 1.5 feet away, and after 60 seconds, the dog is 4 feet away. So I know those 2 points need to be on my graph. In this story, we've got the dog walked around for the first minute. So we've talked about a lot of different possibilities of what walking around the first minute can look like. So your line maybe does that. As long as your line does not curve backwards, or as long as your line does not go above, like that. As long as your line does not go above 5 minutes, you should be okay. It should not be up here. So I've got this as a possibility of what walking around the first minute could look like. The second part says, and then laid down until the owner returned. So this is, again, where we have to think about what does this mean for time and distance. And if you think through that, you're going to realize if the dog is laying down, time is still going forward. So my line needs to go forward. But if the dog is laying down, that distance is not changing. So the only option, you can have whatever you want for this first minute, but after 1 minute, your dog needs to lay down and stay 4 feet from the post for the rest of the time. Your line cannot, this is not okay what I'm going to do. Your line cannot go down here to lay down because that means all at 60 seconds, right? The dog was in all of these different places. The dog teleported from 4 feet to right next to the post. That's not okay. And our line doesn't need to go down to 0 for the dog to lay down. The dog can lay down 4 feet from the post. So we need this horizontal part of our graph to show the dog is laying down. The pink part is the dog walking around, and then the green part is the dog laying down. Again, we're going to look at a lot of graphs in this unit and create a lot of graphs ourselves. So this is just the first part of a lot of conversations about these. Some parts I would emphasize, though, that are going to be true for most, if not all of these graphs, is that idea of use these labels to help you make sense of the story. So as I was reading through all of these descriptions, for example, the dog's laying down, I'm thinking about what does that mean about time? What does that mean about distance? And the other part that we mentioned is this idea of you can't go backwards in time. My line can't ever curve back around, especially when you're talking about time. But in a lot of these situations, it would not make sense for it to go back. The final thing I want to do with our story about this dog is connect it to what we've been talking about with functions. So the first thing I want to think about is we can just look at this graph here of day 3. Is this a function? Go ahead, pause the video if you need to think through that question. Would you say this is a function? Why or why not? To help with that question, it might help to identify the input and the output. The input here you can always find on your x-axis. The input here is the time. And output, similarly, you can always find that on the y-axis. That is going to be our distance. And if I want to know if this is a function, I want to go back to our definition of a function. We said a function is a relationship where, do you remember what comes after that? It's the part we underlined in the definition. Each input has only one output. So keeping that definition in mind and what we said the input and the output are, would this graph here be a function? Our answer is yes. Each input at each time, there is only one output. There is only one distance. 60 seconds after the owner left, I can see there is only one output. The dog is 4 feet away. 100 seconds after the dog left, there is only one output. The dog is still 4 feet away. 20 seconds, the dog is 2 feet away. I see that there is only one output. That definition of function also helps explain what we said earlier about how your line can't go backwards. If my line went backwards, if I did something like this, that wouldn't be a function anymore because one input would have 1, 2, 3 different outputs there, and that's not a function. Each input has to only have one output. So all of these days we looked at, day 1, day 2, day 3, they are all functions because each input has only one output. There is one final goal for this lesson, and it's how you can describe these if something is a function. Again, we're going to need to know the input and output. When we talk about function language, it's going to be a phrase that uses, it's going to be a sentence that uses the phrase is a function of. And the way you figure out what words to put in these places has to do with input and output, or your x and your y-axis, or if you had me for pre-algebra, we talk about independent and dependent variables. It's all the same idea. So we said earlier the input of the situation we've been looking at is time. And I should be more specific. Time since the owner left. And the output was the distance. It was the distance from the post. Again, if you had me for pre-algebra, we talked about independent and dependent variables. and identified them from similar stories. The distance from the post is the dependent variable because the distance depends on how much time the dog has been standing there. So if you're already familiar with independent and dependent variables, you can use those two to help you out with this. The phrase you are going to hear, I promise, in every single lesson, and the phrase we have to understand to be able to do these problems is this phrase is a function of. And when I hear is a function of, I think of the words depends on. Like I said, if you've already learned independent and dependent variables, we used that phrase depends on to help us identify the dependent variable. When you see this phrase is a function of, means your output or your y or your dependent variable is what comes first in that phrase, and your input or your x or your independent variable is what comes second in that phrase. So if I wanted to describe this whole thing about the dog using function language, and how you're going to see it described in stories is this sentence here. You're going to see that it says the time since the owner left is a function of the distance from, I just typed that in backwards. I'm so sorry. Look what I'm doing. The output goes first. So I should say the distance from the post is a function of the time since the owner left. I promise you I know this. And so I'll put this down here. We've got the output comes first, and then that phrase is a function of, and then the input comes second. So don't do what I did, which was looking up here and just typing them in this order, because it feels a little backwards. The output should go first in that sentence, and the input should go second. When we read our stories in this unit about functions, you're going to see phrases like this a lot. You're going to see questions that ask you to write something with function language, and that is asking for the sentence here. So we have to know to understand these sentences and to write these sentences, your output goes first and your input goes second. So the final thing I have for this video is I've got two different examples here. For each of these, I want you to read through the story, and I want you to do three things. I want you to first identify the input and the output, because you need to be able to identify those to really be able to write that sentence using function language. So for these two stories here, identify the input, identify the output, and then write a sentence that looks something like this. That is going to be great preparation for the homework for this lesson and literally every single lesson that comes after it in this unit. Go ahead and pause the video now and try it yourself. For our first story, we've got each apple costs $1 if our two variables are total cost and number of apples. I'm going to pause here and say, I first need to identify my input and my output. You can also think about independent and dependent variables. Here, the total cost is going to be your output or your dependent variable, because the total cost depends on the number of apples. That is our input. I've also had students think about, if you were to graph this number of apples, that's what I would want here on my x-axis, and our output, our total cost, I would want here on our y-axis, and use x and y to help them identify these, or independent and dependent variables. Find the way that makes the most sense for you. But we need to know which one is the independent, the input, and we need to know which one is the output to write that sentence. The sentence is going to say then, since our output comes first in the sentence, it's going to say the total cost is a function of the input, is a function of the number of apples. The only correct way to write that sentence is in that order. You can't say the number of apples is a function of the cost. It has to be your output first, is a function of, and then the input. If you had a hard time with this first one, pause the video here and try the second one to get that practice in. But if you are ready, I'm going to put the answer up in 3, 2, 1. In this one, we have Jesus saves $100 each month. Our two variables are the number of months and the money saved. Here, the number of months he's been saving is our input. If I told you he saved for 10 months, you would be able to give me the money saved for the output. We need those again to help us write our sentence. Even if I didn't ask you to identify the input and output, you should do that first because it will help you come up with the sentence, which is the money saved is a function of the number of months. Again, I've got the output first in that sentence, is a function of, and then our input. This, what's up here on the screen, is going to come up a lot in this unit. So I would make sure I've got some examples in my notes, as well as kind of like this formula for writing that function language. There's a lot we covered in this video. Like we said, we introduced the idea of a function. We started looking at graphs of function, and we also started practicing using this function language. All of those things are going to keep coming up in future lessons. So hopefully you've got an idea of what graphs of functions look like, what this function language sounds like, and what a function is to help you in our future lessons. Thanks so much for watching and have a great day.